Hi, I'm Neel.
Hi, I'm Alisen.
Here's our inverting op-amp circuit. So here we have a 12 kiloohm resistor and a 1 kiloohm resistor connected to the negative input, and our positive input is connected to ground. Here we are inputting a square wave of frequency 1 kilohertz and amplitude 250 millivolts because we want a 0.5 volt peak-to-peak square wave. So if we run this, you can see that the square wave is inverted and drastically amplified. This is a screenshot of our inverting amp output when we input a 10 kilohertz, a very high frequency input. As you can see, the output waveform is no longer a square wave, and there are these curves because of a delay. This delay is due to the time it takes to charge the capacitors within the transistors of the op-amp. We can measure this delay through something called a slew rate. So using our X and Y cursors, we've been able to determine the total amount of voltage increasing from here to here and the amount of time delay it takes in microseconds. Then to calculate slew rate, we can simply divide the voltage divided by microseconds and we get our answer. When we input a 0.2 volt peak-to-peak sine wave, we get into our inverting amplifier, we get an inverted waveform that is significantly amplified. We can confirm the gain from this output waveform since its amplitude is much bigger than that of the input waveform. This here is our voltage follower circuit. As you can see, the negative input is connected to the output.
This is our differential op-amp. The black wire is V2 and the red wire is V1. For common mode gain, we set both V1 and V2 to power, which is the same, which means that the difference between them is 0, and the op-amp resistance is infinite. This means that our signal should be 0 because amplifying 0 is still 0, but it's slightly off because there's interference in the circuit. So here we can see that our input amplitude is high and our output amplitude is very low, but since it's so low, if we want to see it, we have to change this to so here we can see the input, but since it's so messy, because it's so small, we average it to 16. To measure the common mode gain, we take the peak-to-peak amplitude of channel 2, and then divide it by the peak-to-peak amplitude of channel 1.